Hello physics students. In the last video, I showed you how you can represent the motion of an object creating graphs, displacement versus time, velocity versus time, and acceleration versus time. In this video, we're going to look a little deeper into graphs, how you can analyze them, calculating either the slope of a graph or the area under a graph. Now the slope we already got into a little bit in the last video and also in SparkLab 1 and SparkLab 2. So I'm going to skip over that with notes, but I just want to remind you that what we learned is if you take the slope of a displacement versus time graph, you get the velocity. If you take the slope of a velocity versus time graph, you get the acceleration. So I'll summarize that later. Today I want to move to the new material, how to analyze a graph by calculating the area under the graph. And I'm going to do that by just doing out an example. So I'll step aside. Now, I'm thinking I might make this graph and put it in the Google Classroom stream. If you see it, you could print it out and stick it right into your notebook. Okay? If it's not there at this point while you're watching this video, then just go ahead and jot that down to the best of your ability. Okay, and write this down. Okay, so the question for this graph, first of all, let me just describe what's happening in this graph. What we see is an object is moving in the plus direction with 4 meters a second. So it's going 4 meters a second at a steady rate for 6 whole seconds. So it's plodding along steady like this in the forward direction. And then what happens is it starts slowing down while still moving in the forward direction. From 6 to 8 seconds, it's slowing down, and then it hits velocity 0, and then it starts going in the negative velocity direction, which is backwards, with an ever increasing faster negative velocity. So then it goes faster, 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 faster. So again, let me do it all at once. Forward, steady for 6 seconds, then slowing down, gets to 0 velocity, then starts going backwards faster and faster and faster. So that's the motion of the object. What we're trying to find for that 12-second motion is we want to first find the distance, then the displacement, then the average speed, and the average velocity. Okay, so that's what the problem is. Now, the average or the distance and the displacement. You don't have to write this down because it's in your reference table, but we have this formula that we can use if we have numbers, not a graph. And if you look at this graph, you can see that there's no acceleration in the beginning because the speed is constant, or the velocity is constant, I should say. So this part of the formula is gone. So to find the distance using a formula, we would just take that speed of 4 and multiply the time over which it applies, which is for the first 6 seconds it's going 4. So we do 4 times 6. And get 24. Now, what that is, if you think about it, if we forget about formulas now, just think of geometry. If we have this distance and this, and we multiply those two together, what we're calculating is the area of that rectangle right here. And that's the name of the game for distance. What we do is we calculate areas. And the area is between the graph, plot, and the t-axis. So for example, one area is a rectangle like this. Oops, let me go here. And I'm going to call that area 1. Okay. Another area is right here between the plot and the t-axis. Have to write a little smaller here, area 2. And then the third area is between the plot and the t-axis. So, for part A, the distance equals those 3 added together. Because remember, if you go jog 2 miles this way and then you turn around and jog 2 miles back home, you go 4 meters. It doesn't matter that you're going backwards. So the fact that this is going backwards for distance, we just still add it to the other areas. So we would say now that this is area 1, area 2, and area 3, all added together. And so, the area of a rectangle is just base times height, as I already said. So this is going to be the base of 6 seconds, and the height is 4 meters per second. And then I'm going to add to that the area of this triangle right here. The area of a triangle is 1/2 the base, and if you look at the base of the triangle, it goes from 6 to 8 seconds. That's 2 seconds wide. And the height of the triangle is 4 meters per second. And the backwards triangle, the backwards motion, again, we add because distance doesn't ever get less with more motion. So that's, again, a triangle. So the area there is 1/2 the base, which is from 8 to 12 seconds, or 4 seconds. And the height of that triangle, well, if you look carefully, not so clear on this board, but it goes down to 12. So that's 12 meters per second right there. Some people say, well, wait a minute, isn't that negative 12 meters per second? Well, then you're having a negative distance in the end. And that doesn't happen, okay, with distance. So this is 24. This is 4. And that's 24. So that is 52 meters of motion, of distance. Okay, so that's the distance the object moved. Okay? Okay, the next thing we need to calculate is the displacement. Okay? Now remember, displacement is the net motion. So if I move forward 10 meters and then I move backwards 8, the displacement is net 8 forward motion. So when I move backwards that 2 meters, I have to factor that in as a negative quantity with displacement. So we could express that this way. We would take area 1, area 2, and area 3, and the two areas now above the t-axis count as positive. And the backwards motion has to be factored in as negative. So if we go back to the line above, we don't have to rewrite all this. We know we have 24, 4, and 24. So what that would be mathematically, here, if we substitute that in, we could say we had positive 24 meters, and then positive 4 meters, and this, which is negative 24 meters. And so if we press that on a calculator, we get that the displacement is equal to positive 4 meters. Positive indicating that the object had a net forward motion of 4 meters. You could also, if you want to, distinguish displacement by putting that little half arrow over the top, but it's not necessary. In textbooks, they often just use D, but they bold it. But if you just call it D, we know that it's displacement because that's what it was asking for here. Okay, now, average speed and average velocity. A mistake a lot of students make is they say, I know how to do average. I add them up and divide by 2. So for average speed, I could do 4, and then I ignore the negative because it's speed. 4 plus 12 divided by 2, which is 8. And for average velocity, I add up with this being a negative. 4 plus negative 12 divided by 2 gives me 4. Wrong, not correct. Remember I said back when we were learning these definitions, if they ask you for average speed or average velocity, do not take an average. It kind of is misleading. You see the word average and you automatically think, oh, add it up and divide. By how many? But the way you do it with speed and velocity is for speed, average, and you could even put a bar over the top to mean average. You would use distance over time. And the distance is 52 meters over 12 seconds. Okay? So that is 4.33 repeating. So if I do it here, I'm going to run out of room. So I'll do it right here. I'll say that V equals 4.33 meters per second. Okay? That way I could fit all the answers on one board without erasing. All right, the next thing, the average velocity. Now what we do for average velocity is we do displacement over time, not distance over time. And the displacement was positive 4 meters. And the time was 12 seconds. Do 4 divided by 12 and you get positive 0.33 meters per second. Okay, I'll pause the video a minute to give you a chance to copy all this down. Okay, so that is how you do it. You calculate the area. Imagine between the graph and the t-axis, what's sandwiched between? Rectangles or triangles? Here's the graph, here's the t. Now that's a triangle right there. And then the graph goes down like this, the t-axis, so that makes another triangle. And then you calculate those areas, either length times width for rectangles or 1/2 base times height for triangles. And then for distance, you add them all up because backwards motion doesn't make your distance go down. You're still going up in distance. For displacement, any area below counts as negative, any area above counts as positive. And then you sum up that way, okay? And then average speed and velocity, just do those answers that you got. This distance over time for speed or displacement over time for velocity, and you get your results that way, okay? Put those maybe there, okay? So now that's the calculation for what we can do with the velocity versus time with area. What I'm going to do now is I'm going to erase this and create a summary of all the things that you could do with the various graphs that we studied. Okay, so you're presented a graph. One of the things you could do, be required to do, is just read points off the graph. like that graph I erased, you might be asked, well, what is the velocity at 4 seconds? And then you look and you say, oh, 4 meters a second. What is it at 12 seconds? Oh, negative 12 meters per second at 12 seconds. So that's the easiest thing you could do. Or you might have to calculate slopes or areas. Oops. So here are 3 possible graphs you might be given. You might be given a displacement versus time, or velocity for time, or acceleration versus time. If you want to find the velocity from the displacement, we learned this in Spark Lab 1. What you do is you calculate the slope of a displacement versus time graph, and it gives you the velocity. I'll sketch something in temporarily. The slope is rise over run, or y, which is d, over x. The distance over time is velocity, right? So that's slope of this gives velocity. We also learned in Spark Lab 2 that if you have a velocity graph, maybe like this or something like that, and you do the slope of that, it's change in velocity per change in time, that's acceleration. So the slope of this gives us acceleration. Okay. Now, what we learned today is that if you take the area of this, it gives you distance or displacement depending on how you sum up the area. So if you have a velocity graph, you take the area under that graph and it gives you distance or displacement. The example we didn't do is that if you have an acceleration graph and you do the area under that, that gives you actually not the velocity, but it gives you delta V, the change in velocity. Okay. So this is a summary. Displacement slope gives you velocity. Velocity slope gives you acceleration. Area under acceleration gives you the change in velocity. Area under the velocity gives you the distance or displacement. So these are the 3 things that you could do with graphs. Read points, calculate the slope, or calculate the area. All right, so that's it for our graphical analysis video. I'll see you in the next physics video.